Hello, everyone. And there you find yourself reading chapter 15 already. And this is also the chapter that we're going to discuss in this lecture. Importantly, so far we studied markets in isolation, and this week we are going to look at markets that are interconnected. We're also going to look at social welfare functions, at the concept of Pareto efficiency. When can we claim that a market operates efficient, and what measure do we have and use to measure efficiency? And we're look at exchange efficiency in markets, and we're going to discuss two fundamental theorems of welfare. So, what is their meaning and what are their implications? When you consider a market in isolation, as we have done so far, we call this partial equilibrium analysis. You look at the equilibrium in that market only, and you assume that it's isolated from any other market. But in the real world, most markets are linked. If there's a demand shock or a supply shock on one market, that often not only has implications for the equilibrium in that market, but also for the equilibrium outcomes on other markets. And this is what we're going to study in this chapter. For example, if there's an increased labor demand from one industry, then it will increase the wage for all workers, regardless of the industry that they work in. So, as an example, at the moment, the government needs a lot of people for the vaccinations, so they hire a lot of people. But now the pubs have reopened and there's a shortage of personnel for staffing the pubs and to supply people with the drinks on the terraces. So here the labor market is important in both markets, and a demand for labor in one market has implications for the price of labor in other markets as well. And ultimately also it has implications for the price of your beer. So in this chapter we introduce what we call general equilibrium analysis. And this is the study of market behavior that incorporates cross-market influences to determine the equilibrium. And let's start with an example. So this is again a mathematical model with equations, and we're going to solve this. So suppose the demand for corn is given by 20 minus PC, which is the price of corn, plus PW, which is the price of wheat. And here already you see the new element that the demand for corn, the quantity demanded, not only depends on the price of corn, but also on the price of wheat. And there's a plus sign here. You can see that an increase in the price of wheat increases the demand for corn. So apparently these two are substitutes. And the demand for wheat is given by a similar equation. So the demand for wheat is given by 20 minus PW. So it's decreasing in the price of wheat, but increasing in the price of corn, plus PC. And the supply of each is a very simple equation here. It's upward sloping in price, as we would expect, but the supply function is just identical to the price. So the supply of corn is identical to the price of corn, and the price of wheat determines the supply of wheat. So we have two markets here, the market for corn and the market for wheat, and we have to determine the equilibrium price and equilibrium quantity in both markets. And as you can see, these two markets are connected in their demand functions, because the demand in one market is also dependent on the price that establishes on the other market. So let's do this. What is the equilibrium price for wheat? So we have this demand function for wheat and the supply function, and in equilibrium, supply needs to equal demand, just like before. So when we equate the two and we solve, then we get an expression that still contains one or two unknowns. So if we solve this resulting equation over here for the price of wheat, we see that the price of wheat is positively dependent on the price of corn. But at this point, we still don't know the equilibrium price of corn, and we don't know the equilibrium price of wheat. But if we know the price of corn, then we would also know the equilibrium price of wheat. So how to make progress here? Well, realize that here we derive this equation by only looking at the supply and demand for wheat and equating the two. And that gave us one expression with two unknowns, the two unknown prices. But what happens if we do the same for the market for corn? So the equilibrium price for corn is also establishes by equating the supply and the demand for corn. So here we have the demand for corn, here we have the supply of corn. When we equate these two, then we arrive at an expression that gives us the price of corn as a function of the price of wheat. So PC is 10 plus PW over 2. That is our second equation. So now we have two equations with two unknown prices, and we can solve this. So these are the two equations that we derived by equating supply and demand in each of the two markets. And now we can insert the expression for the price of wheat into our second expression in the PW. So we replace the PW in our second expression by the expression that we obtained for the price of wheat in the first equation. So of course you can do it the other way around. You could also choose to replace the PC in the top equation by the expression at the bottom. But let's do it like this. So when we insert the 10 plus PC over 2 into this expression where currently there is this PW, and we get this expression here in the top. And when we simplify, then you arrive at PC is equal to 10 plus 10 over 2, so 5. 10 plus 5 is 15. And PC over 2 divided again by 2 is PC over 4. And we can solve this expression for PC by bringing this term to the left-hand side, and you get PC minus 1/4 PC gives 3/4 PC needs to equal 15, and solving for PC gives you the equilibrium price of corn being equal to 20. So when the equilibrium price of corn is 20, then we can easily derive the equilibrium price of wheat, because we already have a function that gives us the price of wheat as a function of the price of corn. So we simply replace the PC over here by the 20, and you get that the equilibrium price of wheat is 10 plus 20 divided by 2 is 20 as well. So both the equilibrium price of corn and wheat is 20 in this case. Of course, it's a coincidence that they are both equal to 20. This is just a result from our expressions of the demand and supply functions in the two markets being very symmetric. If you would make them less symmetric, then the equilibrium prices would probably also be different. And now you can plug in the equilibrium prices in either the demand or the supply function in each of the markets. Again, it doesn't matter which one you take, because in equilibrium supply equals demand. So we had these very simple supply functions saying that the supply of wheat is identical to the price of wheat. So it makes sense to use that one in order to derive the equilibrium quantity of wheat. So equating that gives us that the equilibrium quantity of wheat is 20 million bushels, and the equilibrium quantity of corn is 20 million bushels as well. And that completes our practical application. So this is the first example of general equilibrium theory that you got, and this is pretty straightforward. So it's a very useful tool, because in this way we can compute the effects of a change in one market, so a shock to the demand or the supply in one market, on the equilibrium outcomes in another market. And we did here an example where the dependency between the two markets was via the demand functions. So the demand for one good positively dependent on the price of the other good, the price in the other market. Of course, you could just as well let this interconnectedness run via the supply function. But How you model it in practice should depend on the real life phenomenon that you have in mind. So does it make sense that supply is interconnected, or does it make more sense to model demand as being dependent on each other? But in solving, it doesn't make a difference. It's conceptually the same. And this already brings us to the first quiz of this lecture. And as you will see, it's very similar to the example, but it's a little bit more intricate here because we have, again, two markets. So we have the market for rice. The demand for rice, again, is not only dependent on the price of rice, but also on the price of potatoes, which is the second market that we consider. And likewise, the demand for the potatoes is not only dependent on the price of potatoes, but dependent on the price of rice as well. But to make matters a little bit more interesting, we have here an example where also the supply of rice and potatoes is dependent on the price that establishes in the other market. So the supply function of rice not only depends on the price of rice, but also on the price of potatoes, and the supply of potatoes also depends on the price of rice. You already can see by the way this problem is set up that the demand and the supply functions in the two markets are again very symmetric. So you would expect that if you would solve this problem, the equilibrium price in the market for potatoes would be identical to the equilibrium price in the market for rice, and also the quantities will be the same. But I leave it up to you to determine what that equilibrium price and what that equilibrium quantity in both markets are. So, how did that first quiz question go today? So, I will give you the answer, and the solution method is exactly as what we did in the first part. So, I repeated here the supply and the demand functions for both the market for potatoes and rice, and we know one thing: in equilibrium in both markets, supply needs to equal demand. So that gives us the following equations. If we look at the market for rice and we equate supply and demand, we get an expression of the price of rice as a function of the price of potatoes. Similarly, we can do this for the market for potatoes, and we get an expression of the price of potatoes as a function of the price of rice. Now we can replace, and here we should have an R. This PP should be PR, of course. And we could replace the PR on the right-hand side here by the expression that we found for the market for rice, and then solve for the price of potatoes. If we would do so and then plug back in the solution for the price of potatoes in the expression for the price of rice, if you do this correctly, then you will get that the equilibrium price of both rice and potatoes is equal to 50. So as predicted, because of the symmetric setup of the problem, the two prices are the same in equilibrium. And then you can plug in these two prices in either the supply and the demand, or the demand functions of the two goods, in order to get the equilibrium quantities. Now, it's very nice that we are able to find the equilibrium price in quantities in multiple markets if we study them together, but we also want to know whether the outcome that we get, the equilibrium outcome, to which extent this is a desirable outcome. So let's look a little bit at the equity and efficiency of the equilibrium outcomes. And these are two different things. So as economists, we often want to figure out what outcome is best for society as a whole, and this is something that we have in common with the non-economists in society, who also want to find out what is best for society as a whole. But of course, to find out what is best, you need to come up with a metric on how to measure different outcomes in terms of goodness. So, and this is important because if you, as an economist, have to advise the government who proposes to make a certain change to for example, to introduce a tax, to give a subsidy, to change the structure of a market, then you want to predict what is going to happen to the equilibrium outcomes, and you may also want to say something about whether the new equilibrium outcome is better or worse, or whether certain groups in society benefit from it and some others don't. So in policy advice, this is quite important. But how do we determine what is best for society as a whole? Because that's a rather vague concept. So in some sense, we need to aggregate the utility levels of all the individuals in society. So if the utility of a person is an indicator of his well-being, then the sum of all the utilities should be an indicator of the well-being of society as a whole. But there are different ways to look at this aggregate utility. And we need to go beyond the utility function of an individual, but we need something like a social welfare function. So there are different approaches that we can use here, and the easiest thing to do, at least conceptually, is to just add up the utility levels, and then you arrive at what is called a utilitarian social welfare function. So that social welfare function, W, is very simply the utility, the aggregate utility of all individuals in society. And notice that in this expression as is given here, all people in society are weighted equally. Everyone is equally important. However, we run into a problem here because we already found out that, well, absolute utility levels don't mean anything. They don't represent the units of plane of pleasure that people experience. They just are a measure to rank people's observed choices. So, but we can do monotonic transformation, so we can multiply all utility levels by 2. The ranking of the different elements in the choice set doesn't change, so in fact it doesn't mean anything. So this is a problematic social welfare function. And what we need to do is to translate all these utility levels back into monetary terms. So if you prefer A to B, how much money are you willing to give up in order to have A instead of B? Once we know that one individual is willing to give up $2 and another person willing to give up $3, then we know that together these individuals are willing to give up $5. So bringing utility levels back to monetary terms allows us to aggregate them in a way that is meaningful. And this is exactly the approach that we already taken in computing the consumer surplus, which measured the difference between what people actually had to pay for an item and what they were willing to pay. So, and also with the producer surpluses that we studied in the chapter last week. But there are more social welfare functions possible. As said in the previous one, we just aggregated utility of all individuals in society, but you could also state that for society it's important to look after the people who are worst off. And that brings you to what is called the Rawlsian social welfare function, mentioned after John Rawls. And this is also the part of economics that comes quite close to the field of philosophy, because when you consider what is best, what is optimal for society, you already come pretty close to questions that are also important in the field of philosophy. So, and John Rawls, of course, is also an important name in that field. Now, what does the Rawlsian social welfare function look like? The idea is that you want to make the worst off individual in society as well off as possible. It's a very egalitarian welfare function, and it has the form W is the minimum of the utilities of the different individuals in society. So this social welfare function doesn't increase if you increase the utility of any individual in society that doesn't happen to be the worst off individual in society. W only increases if you make the person with the lowest utility the person who is worst off, if you make that person better off. Then you really attained an increase in social welfare. So this utility function, or this social welfare function, is very egalitarian. So it may sound very attractive, but of course this one has also problems because it's very hard to implement. And why is it hard to implement? Well, you need to find an individual in society who is worst off, and only then you can try to improve social welfare. That may be a very daunting task in practice. But as a benchmark, it's good to keep it in mind, the different social welfare functions. So, yeah, it's very hard to agree on a social welfare function. So that makes it a matter of ongoing debate, which is also what philosophers like a lot. So it's really hard to reach a final conclusion. So which social welfare function is best? And you can imagine that the Rawlsian approach resonates more with some political parties than with others. Other political parties may have different social welfare functions in mind, either explicitly or implicitly, and it's very hard to agree on the right one. Is there a way out? Yes, there is a way out, and Pareto tried to find a way out of this debate. He took a different approach, and the question that he asked is, okay, let's think of the minimal condition that a social outcome should at least satisfy. So he asked the question, okay, can we formulate a condition that is the bare minimum that a social minimum should satisfy? And if that is not satisfied, then certainly it is socially not a good outcome. And he came up with situations where Pareto, well, he didn't call them that, but they are named after him. So he thought of a situation where you could make at least one person better off without making anyone worse off. And he figured that as long that is the case, then you did not reach yet an efficient outcome. And these are called Pareto improvements. As long as Pareto improvements are possible, as long as it is possible to reallocate resources in such a way that you make at least one person better off without making anyone else worse off, then you are able to make an improvement, a Pareto improvement. So the old allocation could not be an optimal outcome. And that's the fundamental idea that he came up with. So if the Pareto improvements are possible, then clearly it's not desirable from a welfare point of view. And you reach a state of Pareto efficiency when no Pareto improvements are possible anymore. So at a Pareto efficient outcome, these outcomes satisfy the condition that it's not possible to make, by reallocating resources, to make at least one person in society better off without making anyone worse off. Sounds good. This is something that all people can more or less agree on, that you should at least exhaust all possibilities to make people better off if it doesn't do any harm to other people. At the same time, this is a bare minimum. It's a very weak condition on outcomes. And I will tell you after the quiz why this is the case. So, but before that, we have a second quiz. and we consider two different allocations. In the first allocation, person A gets 3. So, and also think of getting 3 units, but also that these 3 units represent a utility of 3. Person 4 gets 4 units and person C gets 5. In the second allocation, person A gets 2, person B gets 5, and person C gets 7. So then looking at the different welfare functions, which of the two allocations is best if first we take a utilitarian perspective, and second, which one is best if we take the Rawlsian perspective? I think this is a quite straightforward question. If you're not able to answer it, then you should go back a couple of slides. Okay, and here's the answer to the quiz. So if you take the utilitarian perspective, then you simply sum the different utilities. So in the first allocation, you get to a sum of 12, and in the second allocation, you get to a sum of 13. So from a utilitarian perspective, you should prefer the second allocation. If you take the Rawlsian perspective, you look at the person who is worst off, which in both cases is person A, but in allocation 1 he gets 3 units, and in the second allocation he gets only 2. So the worst person is better off in the first allocation. So from a Rawlsian perspective, using the Rawlsian social welfare function, you should prefer allocation 1. So far we discussed Pareto improvement and Pareto efficiency, so how you can reallocate units of goods, making some people better off without making anyone else worse off, but we only discussed it in a rather abstract way. And we're now going to do some specifics here, also relating these Pareto improvements to the underlying utility functions of the individuals involved. And this again brings us back to the indifference curves that we studied at the beginning of this course. So what does exchange between individuals improving the outcomes of both look like? So let's consider Alice and Bob, and they have each an endowment of apples and bananas. And in this society consisting only of Alice and Bob, there is a total of 10 apples and 8 bananas, but Alice starts with an initial endowment of 3 apples and 5 bananas, whereas Bob starts out with 7 apples and 3 bananas. So Bob has more apples, Alice has more bananas. Question is this a Pareto efficient allocation? Well, it's impossible for us to answer this question because so far we don't know anything about Alice and Bob's preferences. Specifically, we don't know to which extent they like apples and bananas and are willing to trade apples for bananas or vice versa. So let's first consider the preferences of Alice by just writing down or graphing a couple of indifference curves. So on the x-axis we have the apples, and we have the 10 here because in total there are 10 apples available in this society. In total are 8 bananas available in the society, so we put that here on the y-axis. And these pinky curves are some indifference curves of Alice. So you can see that they're nicely convex, no corner solutions here. Probably Alice will prefer some mixture of apples and bananas because the indifference curves are nicely convex. Now then we have Bob, and Bob also has preferences for apples and bananas. He also has nicely convex indifference curves, so judging from the indifference curve, we don't expect Bob to prefer extreme outcomes of allocations with only apples or only bananas. But yeah, studying these two individuals in isolation is one thing, but in order to get to Pareto efficiency and to study that, it's optimal to put both indifference curves of both individuals in one graph. So this is what we are going to do. And we are going to flop the graph by Bob 180 degrees. So we just twist it around and then put it on top of the graph for the indifference curves of Alice. And you get a resulting figure, which in the first instance may be hard to read, but once you get the idea, it's quite simple. So as before, Alice's utility is increasing when she moves from the origin towards the top right corner, because then she gets more of everything. But for Bob, notice that we twisted his indifference curves. So this is the point where he gets 0 bananas and 0 apples, but Alice would get all of the apples and all of the bananas. And Bob's utility is increasing as when the allocation moves from the top right to the bottom left. So his utility is increasing if you move in that direction. So this box, which is called the attribute box, represents all allocations of apples and bananas in this economy that are possible between Alice and Bob. So for example, at this point over here, you have the allocation. Alice has 8 bananas, Bob 0. Alice has 10 apples, Bob 0. And if you would be at the point, say, somewhere over here, at this point, you would have Alice has 4 apples and say 6 bananas, and Bob has the remaining bananas, so he will have 2, and he will have 6 apples. So all the points in this box, this attribute box, you can just make dots, and each dot will represent an allocation of apples and bananas between Alice and Bob. And that allows us, together with the indifference curves that are shown, to say which of these allocations, which of the dots are Pareto efficient. So for example, if we take the point A, this is the initial allocation. So this is the allocation where Alice starts out with, I think it was 3 bananas or 3 apples and 5 bananas. And Bob started out with 3 bananas and then 6 apples. So Alice has 3 apples, 5 bananas, and Bob has the remaining bananas. So he has 3 bananas and he has 7 apples. So point A is the initial allocation. This is what they have to start out with. And then the question is, are Pareto improvements available? Can they trade apples and bananas in such a way that makes them both better off? Better off within the context of our course means, can they reach an allocation that gives each of them a high utility? Well, you can see that at the initial allocation A, Alice is on this indifference curve because it runs through the initial allocation, and Bob is on this indifference curve that also runs through the initial allocation. So can they be made better off? Well, to find the answer, let's zoom in a little bit. So now we zoom in on this area that are between these two indifference curves, which is this area. And you readily see that if instead of allocation A, Bob and Alice would reach an allocation that is within these two indifference curves, then both of them would arrive at a higher indifference curve. So if you look at the point where the arrow now is, and you would draw the indifference curve of Alice that runs through this point, then that indifference curve would be one associated with a higher utility level than the initial indifference curve. And the same for Bob. The indifference curve that runs through this point over here would be associated with a higher utility level than the indifference curve that runs through the initial allocation A. So, by moving to the southeast, both would become better off. All these allocations are associated with higher indifference curve, both of Alice and of Bob. And it is feasible as well because the Edgeworth box gives all allocations of apples and bananas. And Bob and Alice have these bananas, so they can freely trade among the two of them. So all such moves would constitute a Pareto improvement. Natural follow-up question here is, when are all these mutual beneficial trades exhausted? So is there a point, or are there points where no further trades can be imagined that make both individuals better off, or that make at least one of the two better off without making the other worse off? Answer is yes, such allocations are there. And more specifically, those allocations are the allocations at which the indifference curves are tangent to each other, like in the point A that is given in the graph over here. So here you can see that at this allocation, the indifference curves are tangent, and if you would move in this direction, you would make Bob better off, but you would make Alice worse off. And if you would move in this direction, you would make Alice better off, but Bob worse off. And also, if you would move somewhere here, you would make both individuals worse off. So a point B over here, if you draw the indifference curve that runs through them of Alice and Bob, both of the indifference curve would be associated with a lower utility level than the two indifference curves that have been drawn through point A. So we have reached an outcome of Pareto efficiency when the slope of the indifference curves are equal. Now, when does it hold? It holds when the marginal rates of substitution are the same for both consumers, for both Alice and Bob. So in formula, we reached an efficient allocation if the marginal rate of substitution of Alice equals the marginal rate of substitution of Bob. So the ratio of the marginal utility of apples and bananas of Alice must be equal to the ratio of the marginal utility of apples and bananas of Bob. But we know from the previous lecture that when Alice is confronted with the price of apples and bananas, she will buy from her budget just the amount of apples and bananas such that the marginal utility of apples and bananas, the ratio, is equal to the price ratio of the two goods. Bob, being in the same market, being confronted with the same prices of apples and bananas, will do the same. He will buy apples and bananas in such a way that his ratio of marginal utilities of apples and bananas equals the price ratio of the two. So they equate the marginal utility ratios, the marginal rates of substitution, each independently to the same price ratio. And by equating them to the same price ratio, this ensures that also the marginal rate of substitution of both individuals must be identical. So, to reiterate, given prices of apples and bananas, each consumer independently will make sure that his or her marginal rate of substitution equals the ratio of the prices. That implies that everyone's marginal rate of substitution will be equal because all individuals in society face the same prices. So, by the price mechanism, we will reach a Pareto efficient outcome. And this is one of the wonders of economic theory, that it shows you that if you just have the price mechanism and everyone is free to buy and sell goods giving his or her budget, the equilibrium allocation that will be reached will be the one that is Pareto efficient. So can we cheer, relax, and really be happy about market outcomes? No, not really, because the efficient outcome is not unique. There's more than one efficient outcome. So there are many points in this Edgeworth box, many dots, many allocations that are Pareto efficient. So if again we look at the situation of Alice and Bob, then there are multiple points in this attribute box where the indifference curves of the two individuals are tangent to each other. So in this graph here, there are 3 of these points depicted. So these 3 green points are 3 Pareto efficient allocations, but in fact, in a setting like this, you'll have an infinite number of them, and you can connect all the Pareto efficient allocations. So this green line that is given here is the set of all Pareto efficient allocations. And the green line has a special name. This is called the contract curve. It's a very nice result, but it raises another question, and that is, okay, given that we have a set, this green contract curve, an infinite set of Pareto efficient allocations, which one is optimal? They're all Pareto efficient, so this is also why I call the concept of Pareto efficiency a rather weak concept, because it gives us many efficient outcomes, and it doesn't allow us to distinguish which of these efficient outcomes is better or worse. And you can see that some of these efficient outcomes, despite being Pareto efficient, are not very nice for all individuals in society. So if you look at the extreme cases, you can see that the origin at Alice and also the origin at Bob both belong to the Pareto efficient set. So if you have as an initial endowment the situation where you give Alice all the bananas, so 8 bananas, and also all the apples, 10 apples, then this outcome is Pareto efficient. Bob doesn't receive anything, but it is efficient because there's no trade possible that can make Bob better off while not making Alice worse off. Because in any case, Alice needs to give away something to Bob, getting nothing in return. So in given Alice preferences, that certainly will lead to a decrease in her utility. So the extreme outcomes where one person gets all and the other one person gets nothing is also a Pareto efficient outcome. So that's the situation that is drawn here. So outcomes may be efficient, but from other considerations that you may have, you may not deem them fair because they're not very egalitarian. So Pareto efficiency does not have anything to say about the fairness of a certain outcome. That brings us to the third quiz, which is to consider an attribute box, and we have Lou and Thelma, and they are the 2 persons in this economy, and there are also 2 goods in the economy, soda and pizza, and there are 3 questions to answer. So at point A in the attribute box, which is given here, how much soda and pizza does Lou have? How much does Thelma have? Question B, suppose that taking point A as the point of departure, and we take 2 pieces of pizza from Lou and give them to Thelma, and at the same time 2 sodas from Thelma and give them to Lou. Is that a Pareto improvement? Third question, very similar. Suppose that we only transferred 1 unit of each. Is that a Pareto improvement? And explain this by plotting new indifference curves. So to my left, you see the 3 questions of the quiz, and now I will give you the 3 answers. Starting with question A, which is, of course, a simple question. You can just read it from the graph, but this learns you how to read attribute boxes. And you can see that if you look at the axes that are relevant for Lou, which are the red colored ones, then at point A, Lou has 3 pizzas and 1 soda, And at the same time, at point A, at this allocation, Thelma has 1 pizza and 3 sodas. And to that end, you should take the origin here as the top right corner and then follow the blue axis. Now, once you know how to read an attribute box, you can also solve question B and C. And question B is, well, we exchange 2 sodas from Thelma to Lou and 2 pizzas from Lou to Thelma. So we go from allocation A to allocation B. Is that a Pareto improvement? No, not really, because point A and B, these both allocations have in common that Thelma and Lou are on the same indifference curve. So no one gets better off, no one gets worse off, but it's not a Pareto improvement in the sense that at least one of them gets better off without anyone getting worse off. Then question C. Suppose now we give one of Thelma's sodas to Lou and one of Lou's pizzas to Thelma. Then we go from allocation A to allocation C, which is the green dot given over here. And that allocation, both Thelma and Lou have 2 pizzas, and they also both have 2 sodas. And as you can see, if you compare it to the old indifference curve associated with allocation A, which is for Lou UL1, then the new allocation C is associated with a higher indifference curve UL2, the red one that is depicted over here. So the new allocation certainly made Lou better off. But it also made Thelma better off because in the old allocations she reached a utility level UT1, and at the new allocation point C she can attain a higher indifference curve associated with a higher utility level UT2. So both are better off, and point C is a Pareto improvement compared to the initial allocation A. And that completes this quiz question and the answer to the quiz question. Then, naturally, the section 15.3 in the book is followed by 15.4 and 15.5, but in this course we skip those 2 sections and we go right away to what has been written down by the authors in section 15.6. So that brings us to the holy grail of microeconomic theory, the welfare theorems. And there are 2 of them, and they are called the first and second welfare theorem. So what does the first welfare theorem say? It says that perfectly competitive markets distribute resources in a Pareto efficient way. Sounds great. Of course, we already know the limitations of a Pareto efficient outcome, but at least this theorem informs you that if markets are perfectly competitive, and what that means, we will get to that. If they are perfectly competitive, then resources will be distributed in a Pareto efficient way. We don't have to do anything. The outcome that will be reached, if we leave it to this market, these perfectly competitive markets, will be Pareto efficient. That's the guarantee. Then the second welfare theorem says that any Pareto efficient outcome, so any green dot on this contract curve, is a general equilibrium outcome for some initial allocation of resources. So this means that you might, as a government, have a preference for one Pareto efficient outcome over the other. So on this green contract curve of Pareto efficient outcomes, you may have some allocations that you prefer more than others. What the second theorem says is that any point that you can select can be reached if you just allocate the initial resources in a certain way. So any dot on the contract curve, any Pareto efficient outcome, is a general equilibrium outcome for some initial allocation of resources. And this is what you have to take for granted. This also holds if we take production into account. So in our treatise of this chapter, we looked at Alice and Bob with a given initial endowment. They didn't have to produce the bananas or apples themselves. So we took out the production side. Section 15.4 and 15.5 say more on that. But here you can take it to granted that if we would incorporate the supply side, the production, then this would continue to hold. Hence, the market mechanism will ensure that one of the best outcomes is achieved in terms of Pareto efficiency. And there's no need for governments to intervene. So for all of the stories about big governments and taking moonshots, be careful. Now the next slides, they show you how the price adjustment process may work. So this is just to give you some intuition. So we're back to Alice and Bob, and we're back to the initial allocation of apples and bananas. So this omega denotes the initial allocation, which is this big red dot that you see. So it's a factor saying that initially Alice is endowed with 7 apples and 2 bananas, and Bob is endowed with 3 apples and 6 bananas. So now suppose that both of them are confronted with prices. So focus on Alice. There's a certain price for apples and bananas. Her budget is given by the initial endowment. So the initial 7 apples and 2 bananas, this is what Alice has. But she can buy additional bananas on the market and sell bananas on the market, and the same for apples, in order to reach a different outcome. And the market price of apples and bananas is given. So the price of apples is PA, the price of bananas is PB. So the budget line that runs through the initial endowment of Alice, because this is what she has, is this green line that we are given here. And the slope of the line is the negative of the price ratio of apples and bananas, just like before when we studied utility theory. So, and what Alice will do is that, well, given that these are the prices at which she can sell or buy apples and bananas, she's going to look for the point on this budget line that maximizes her utility, that leads her to the highest indifference curve possible. And that point may well be different from her initial endowment. Now for Bob, and now you have to really rotate your head by 180 degrees, or you can do this thought experiment if that's easier to you. So Bob, he started out with, I think it was 6 bananas and 3 apples. So his initial endowment is also given here, and he can also trade apples and bananas given the budget line over here. And if you flop your head 180 degrees, then you can also see that the slope of Bob's budget constraint is also exactly identical to the minus of the price ratio of apples and bananas. So Alice and Bob, they are not on social media in contact with each other. They just go to the market. They observe each independently the market price of apples and bananas, which gives them the possible points that they can reach, because this is their budget line, and they choose each independently the one that maximizes their utility. So what may happen is that Alice will choose this point over here. So apples are relatively cheap, and the slope of this budget line is quite shallow. So this is minus the price ratio PA over PB. So if this is a shallow slope, then the price of apples is relatively low. But compared to her initial endowment, okay, she will sell some apples in order to get some more extra bananas, but not very much. And Bob, he starts out with a lot of bananas, but few apples. So what Bob will do is he will sell quite a number of bananas from his initial endowment in order to buy more apples, because his highest indifference curve that coincides with the budget line is this dot over here. But you can see that the choices of Bob and Alice in the attribute box, they don't coincide. So Alice is here and Bob is here. And what it means is that Alice wants to have this many number of apples and Bob wants to have that many of apples, given the prices of apples and bananas. So this is X Bob, the amount of Bob, the amount of apples that Bob wants at these prices, and this is the amount of apples that Alice wants at the prevailing prices. But as you can see, XA and X Bob for apples exceeds the total number of apples that are available in this economy, because the total number of apples is limited to 10. And now together they demand more than 10 apples. So there's an excess demand for apples at the prices that we observe. At the same time, there's an excess supply of bananas, because Bob wants to sell quite a bit of his bananas and Alice doesn't want to buy that many bananas because bananas are relatively expensive. So there's an excess demand of apples and an excess demand of excess supply of bananas. So both the market for apples and the market for bananas are not in equilibrium at the prices PA and PB. So what should happen? Well, given that apples are in high demand and bananas are in low demand, what should happen is that the price of apples should increase relative to the price of bananas. Well, given that our budget line is the slope of the budget line is the price ratio of apples and bananas, if we increase the price of apples compared to bananas, then the slope of this budget line will become steeper. So we need to increase the price of apples. So we do that. And so we can see that now the slope becomes steeper. It still runs through the initial endowment because it's always possible for Alice and Bob not to trade and to stay at the initial allocation. So we increase the slope by increasing the price of apples, but it continues to run through the initial endowment. And now we observe that at this higher price of apples, it becomes relatively more attractive for Alice to sell some more of her apples for bananas. So this is what she does. And for Bob, it becomes less attractive to trade bananas for apples because, well, the bananas have become relatively cheaper. You cannot fetch as much money for them as before. So we observe that, well, in equilibrium, this is the indifference curve, the highest indifference curve that Alice can reach. The dotted one is the highest indifference curve that Bob can reach, but still the 2 points don't coincide. So what needs to happen? We need to further increase the price of apples, further steepening the budget lines, and we can do that. Still no equilibrium, still excess demand for apples. But if we push up the price of apples far enough, then we will reach the point where the demand for apples by Alice and by Bob in total is exactly identical to the total number of apples that's available in the economy, and the same for bananas. So given the initial endowment omega and given the preferences for apples and bananas of both Alice and Bob, the equilibrium price ratio of apples and bananas is given by PA star over PB star. And it's the price ratio that ensures a Pareto efficient outcome. So independently of each other, Alice and Bob make their consumption choices given the prices that they observe in the market. And if the prices are exactly identical to the prices over here, then both the market for apples and bananas will clear. There will not be any excess demand or supply of any of them. Now, a couple of notes. So in this adaptation process, the utility of Alice has increased in every step where we increase the price of apples, because Alice started out with quite a bit of apples. And if you increase the price of the things that you own compared to the price of the things that you own less, then you become relatively better off. So the utility of Bob decreased. If you compare the final outcome to the initial endowment of W, then you will observe that they both land on a higher indifference curve. So compared to the initial endowment, both are better off in the equilibrium outcome. They also traded free will, so of course they would never change their allocation. They will never go away from the initial endowment if that would make them worse off. And as said, Alice had a higher endowment of apples, so the increase in the relative price of apples increased her purchasing power. So the first theorem of welfare economics says that this Walrasian equilibrium, this combination of prices PA and PB and the equilibrium allocations XA, XB, is Pareto efficient. So the prices will always adjust such that an equilibrium is reached that is Pareto efficient. That's the first theorem of welfare economics. Now, the second theorem of welfare economics brought to this attribute box is that if a certain allocation XA, XB is Pareto efficient, like the one that is given here, then there must exist a combination of prices together with an initial endowment, initial allocation omega, such that this allocation is reached as a Walrasian equilibrium, as a Pareto efficient outcome. So if you choose an initial endowment on the green budget line, or the price line that is given over here, then you are certain that prices will establish an equilibrium outcome that has you land on this Pareto efficient allocation XA, XB. So what is the key implication of the first theorem of welfare economics? Well, it's that the price mechanism will lead to an efficient allocation. So the price mechanism is very forceful, powerful in obtaining allocations that are Pareto efficient. And the second theorem of welfare economics is also important because it tells you that you can separate matters of efficiency from matters of distribution. So you may like one Pareto efficient outcome more than the other one. And the second welfare theorem says, well, you can reach any Pareto efficient outcome that you want, and you can leave that to the price mechanism, but you can just tweak the initial allocation such that you will arrive at your Pareto efficient outcome of choice. So for governments, that's important because it tells them that they can separate the important issue of efficiency, you want an outcome to be efficient, from the other consideration that they may have, like having to care about the distribution, who gets which part of the pie. And you want to be more or less egalitarian maybe there. So the government doesn't have to impose conditions on prices. If it wants to reach a certain efficient outcome, it can just do so by reallocating the initial allocation to different subjects. The welfare theorems are important, but they hold under quite stringent assumptions. So markets need to be perfectly competitive, which implies that firms should not have market power. So they should be price takers. They should not have any power to influence the price that they obtain for their products. And, well, look at Apple, iPhone. Certainly Apple has power to influence the price that it charges for its phones. So natural question is, how does this calculation change if firms do have market power? Other things that we assume is that market outcomes do not generate any externalities. So I buy something from someone else, but it doesn't have any positive or negative consequences to people that are not involved in the transaction. In practice, it often has. There are externalities. Think, for example, of pollution. So if I buy something like a car, and many people buy a car, then the roads will become congested. So my buying a car leads to a negative externality. Other thing is the provision of public goods. So who ensures that dikes will be built? So the benefits of building a dike exceeds my private benefits, but also has a positive payoff to other people. We will deal with that in next week lecture and next week tutorial, because it's, well, an increasingly important topic. Other thing that we assume is that everyone knows everything. There's no asymmetric information. But in many cases in life, there's asymmetric information. So sellers may know more about the product that they want to sell than potential buyers. And also buyers may have much better information about their preferences than sellers have. So far, we assume that there's no asymmetry in information. Fourth condition is that we assume that everyone acts fully rationally. So this implies that people perfectly process the choice possibilities that they have. What happens if people act in a more irrational way? So can firms maybe to some extent benefit from irrational behavior? Do markets still work efficiently if people are irrational and the price mechanism may not rightly reflect shocks in demand and supply? Now, these are all in itself important questions, and also very interesting questions from a modeling perspective. Unfortunately, we don't have time in this course to go into detail on all of them. But any follow-up course in economics will single out one or two of these questions and show to you how the line of argument changes. So what we did in this lecture is we looked at general equilibrium. So we brought the connectedness of different markets into the picture. We looked at social welfare functions and social Pareto efficiency, bringing us close to studying, okay, what is optimal, what is the outcome that we actually want, that society would want, and we introduced the welfare theorems. Next week, we're going to introduce externalities and public goods, so market transactions that generate benefits or losses to parties not directly involved into the transaction. We move then from private costs and benefits, like we considered so far, to social costs and benefits. And we also look at which public policies can be developed and designed to fight these externalities and to deal with them. And what are public goods actually, and what is the optimal provision of public goods? But that's all next week. For this week, we will continue with the tutorial. Good luck with that.